the world of cryptography, storing data in plain text is the biggest risk an organization can take. Encryption has been a staple in the field of data transmission since the 1970s, only further highlighting the importance of security when it comes to sharing messages. Algorithms like the data encryption standard, which is also known as the DES algorithm, and the advanced encryption algorithm, also known as the AES algorithm, have been used for decades in both the consumer and business spaces. Let's understand what is it about these algorithms that make them so reliable even after years of inception and growth in the technical field. We start by learning about what is the data encryption standard algorithm in general. We then cover the origin of this algorithm and how Feistel ciphers played a huge role in the formation of this encryption standard. We cover all the steps in a DES encryption phase and also take a look at the future of DES, especially with other algorithms having entered the market. We have a small demonstration of how the DES algorithm uses a key to convert plain text to ciphertext and vice versa. Moving on, we take a look into the AES algorithm and why it was a necessity and its distinct features. We also cover the working and specific applications of the advanced encryption algorithm in today's IT sphere. Finally, we take a look at the differences between both the DES algorithm and the AES algorithm from a technical and a functional perspective.
DES algorithm stands for Data Encryption Standard. It is a symmetric key cipher that is used to encrypt and decrypt information in a block-by-block manner. Each block is encrypted individually and they are later chained together to form our final ciphertext, which is then sent to a receiver.
DES takes the original unaltered piece of data called the plain text in a 64-bit block
and it is converted into an encrypted text that is called the ciphertext. It uses 48-bit keys during the encryption process and follows a specific structure called the Feistel cipher structure during the entire process. It is a symmetric key algorithm, which means DES can reuse the keys used in the encryption format to decrypt the ciphertext back to the original plain text. Once the 64-bit blocks are encrypted, they can be combined together before being transmitted. Let's take a look at the origin and the reason DES was founded. DES is based on a Feistel block cipher called Lucifer, developed in 1971 by IBM cryptography researcher Horst Feistel. DES uses 16 rounds of this Feistel structure, using a different key for each round. It also utilizes a random function with 2 inputs and provides a single output variable. DES became the organization's approved encryption standard in November 1976 and was later reaffirmed as a standard in 1983, 1988, and finally in 1999. But eventually DES was cracked and it was no longer considered a secure solution for all official routes of communication. Consequently, Triple DES was developed. Triple DES is a symmetric key block cipher that uses a double DES cipher. Encrypt with the first key, delete encryption with the second key, and encrypt again with the third key. There is also a variation of the 2 keys where the first and second key are duplicate of each other. But Triple DES was ultimately deemed too slow for the growing need for fast communication channels, and people eventually fell back to using DES for encrypting messages. In order to search for a better alternative, a public-wide competition was organized and helped cryptographers develop their own algorithm as a proposal for the next global standard. This is where the Ringdial algorithm came into play and was later credited to be the next advanced encryption standard. For a long time, DES was the standard for data encryption for data security. Its rule ended in 2002 when finally the advanced encryption standard replaced DES as an acceptable standard following a public competition for a place. To understand the structure of a Feistel cipher, we can use the following image as a reference. The block being encrypted is divided into 2 parts, one of which is being passed on to the function, while the other part is XORed with the function's output. The function also uses the encryption key that differs for each individual round. This keeps going on until the last step, until where the right-hand side and the left-hand side are being swapped. Here we receive our final ciphertext. For the decryption process, the entire procedure is reversed, starting from the order of the keys to the block sorting. If the entire process is repeated in a reverse order, we will eventually get back our plain text, and this simplicity helps the speed. Overall, this was later detrimental to the efficiency of the algorithm, hence the security was compromised. A Feistel block cipher is a structure used to derive many symmetric block ciphers such as DES, which as we have discussed in our previous comment.
Feistel cipher proposed a structure that implements substitution and permutation alternately,
so that we can obtain ciphertext from the plain text and vice versa. This helps in reducing the redundancy of the program and increases the complexity to combat brute force attacks. The Feistel cipher is actually based on the Shannon structure that was proposed in 1945. The Feistel cipher is the structure suggested by Horst Feistel, which was considered to be a backbone while developing many symmetric block ciphers. The Shannon structure highlights the implementation of alternate confusion and diffusion. And like we already discussed, the Feistel cipher structure can be completely reversed depending on the data. However, we must consider the fact that to decrypt the information by reversing the Feistel structure, we will need the exact polynomial functions and the key orders. To understand how the blocks are being calculated, we take a plain text which is of 64-bit and that is later divided into two equal halves of 32-bit each. In this, the right half is immediately transferred to the next round to become the new left half of the second round. The right hand is again passed off to a function which uses an encryption key that is unique to each round in the Feistel cipher. Whatever the function gives off as an output, it is passed on as an XOR input with the left half of the initial plain text. The next output will become the right half of the second round for the plain text. This entire process constitutes of a single round in the Feistel cipher. Taking into account what happens in the polynomial function, we take one half of the block and pass it through an expansion box. The work of the expansion box is to increase the size of the half from 32-bit to 48-bit text. This is done to make the text compatible to a 48-bit keys we have generated beforehand. Once we pass it through the XOR function, we get a 48-bit text as an output. Now remember, a half should be of 32-bit. So this 48-bit output is then later passed on to a substitution box. This substitution box reduces its size from 48-bit to 32-bit output, which is then later XORed with the first half of the plain text. A block cipher is considered the safest if the size of the block is large, but large block sizes can also slow down encryption speed and the decryption speed. Generally, the size is 64-bit. Sometimes modern block ciphers like AES have a 128-bit block size as well. The security of the block cipher increases with increasing key size, but larger key sizes may also reduce the speeds of the process. Earlier, 64-bit keys were considered sufficient. Modern ciphers need to use 128-bit keys due to the increasing complexity of today's computational standards. The increasing number of rounds also increase the security of the block cipher. Similarly, they are inversely proportional to the speed of encryption. A highly complex round function enhances the security of the block cipher. Albeit, we must maintain a balance between the speed and security. The symmetric block cipher is implemented in a software application to achieve better execution speed. There is no use of an algorithm if it cannot be implemented in a real-life framework that can help organizations to encrypt or decrypt the data in a timely manner. Now that we understand the basics of Feistel ciphers, we can take a look at how DES manages to run through 16 rounds of this structure and provide the ciphertext at the end. Now that we understand the basics of Feistel ciphers, we can take a look at how DES manages to run through 16 rounds of this structure and provide a ciphertext. In simple terms, DES takes the 64-bit plain text and converts it into a 64-bit ciphertext. And since we are talking about asymmetric algorithms, the same key is being used when it is decrypting the data as well. We first take a 64-bit key plain text and we pass it through an initial permutation function. The initial permutation function has the job of dividing the block into two different parts so that we can perform Feistel cipher structures on it. There are multiple rounds being procured in the DES algorithm, namely 16 rounds of Feistel cipher structure. Each of these rounds will need keys. Initially, we take a 56-bit cipher key, but it is a single key. We pass it on to a round key generators, which generates 16 different keys for each single round that the Feistel cipher is being run. These keys are passed on to the rounds as 48 bits. The size of these 48 bits keys is the reason we use the substitution and permutation bounds in the polynomial functions of the Feistel ciphers. When passing through all these rounds, we reach round 16, where the final key is passed on from the round key generator, and we get a final permutation. In the final permutation, the rounds are swapped, and we get a final ciphertext. This is the entire process of DES with 16 rounds of Feistel ciphers encompassed in it. To decrypt a ciphertext back to the plaintext, we just have to reverse the process we did in the DES algorithm and reverse the key order along with the functions. This kind of simplicity is what gave DES the bonus when it comes to speed, but eventually it was detrimental to the overall efficiency of the program when it comes to security factors. DES have 5 different modes of operation to choose from. One of those is electronic codebook. Each 64-bit block is encrypted and decrypted independently in the electronic codebook format. We also have cipher block chaining, or the CBC method. Here, each 64-bit block depends on the previous one, and all of them use an initialization vector. We have a cipher feedback block mechanism, where the preceding ciphertext becomes the input for the encryption algorithm. It produces a pseudo-random output, which in turn is XORed with the plaintext. There is an output feedback method as well, which is the same as cipher feedback, except that the encryption algorithm input is the output from the preceding DES. A counter method has a different way of approach, where each plaintext block is XORed with an encrypted counter. The counter is then incremented for each subsequent block. There are a few other alternatives to these modes of operation, but the 5 mentioned above are the most widely used in the industry and recommended by cryptographers worldwide. Let's take a look at the future of DES. The dominance of DES ended in 2002 when the Advanced Encryption Standard replaced the DES encryption algorithm as the accepted standard. It was done following a public competition to find a replacement. NIST officially withdrew the global acceptance standard in May 2005, although DES is approved for some sensitive government information through 2030. NIST also had to change the DES algorithm because its key length was too short, given the increased processing power of the new computers. Encryption power is related to the size of the key, and DES found itself a victim of ongoing technological advances in computing. We have received a point where 56-bit was no longer a challenge to the computers of cracking. Note that because DES is no longer the NIST federal standard, it does not mean that it is no longer in use. DES is still used today and is still considered a legacy encryption algorithm. To get a better understanding of how these keys and ciphertext look like, we can use an online tool for our benefit. As we already know, to encrypt any kind of data, a key is mandatory. This key can be generated using mathematical functions or computerized key generation program, such as this website offers. It can be based on any piece of text. Let's say the word is Simplilearn in our example. Once the key is settled, we provide the plain text or the clear text that needs to be encrypted using the aforementioned key. Suppose our sentence for this example is "This is my first message." We have satisfied 2 prerequisites, the message and the key. Another variable that goes into play is the mode of operation. We have already learned about 5 different modes of operation, while we can see some other options here as well. Let us go with the CBC variant, which basically means the cipher block chaining method. One of CBC's key characteristics is that it uses a chaining process. It causes the decryption of a block of ciphertext to depend all on the preceding ciphertext blocks. As a result, the entire validity of all the blocks is contained in the previous adjacent blocks as well. A single bit error in a ciphertext block affects the decryption of all the subsequent blocks. Rearrangement of the order of these, for example, can cause the decryption process to get corrupted. Regarding the manner of displaying binary information, we have 2 options here. We can either go with base 64 or the hexadecimal format. Let's go with the base 64 right now. As you can see, the ciphertext is readily available. Base 64 is a little more efficient than hex, so we will be getting a smaller ciphertext when it comes to base 64. Albeit the size of both the formats will be the same. The hex has a longer ciphertext since base 64 takes 4 characters for every 3 bytes, while hex will take 2 characters for each byte. Hence, base 64 turns out to be more efficient. Now to decrypt the ciphertext, we go by the same format. We choose base 64. We copy the ciphertext onto a decryption tool, and we have to make sure that the key we are using is exactly the same. We choose similar mode of operation, and we choose the correct encoding format as well, which is base 64 in this case. As you can see, the decryption is complete and we get a plain text back. Even if you keep everything the same, but we just change the encoding format, it will not be able to decrypt anything. Unfortunately, DES has become rather easy to crack even without the help of a key. The advanced encryption standard is still on top when it comes to symmetric encryption security and will likely stay there for a while.
Eventually, with so much computing power growth, the need for a stronger algorithm was necessary to safeguard our personal data. As solid as DES was, the computers of today could easily break the encryption with repeated attempts, thereby rendering the data security helpless. To counter this dilemma, a new standard was introduced which was termed as the Advanced Encryption Standard, or the AES algorithm. Let's learn what is Advanced Encryption Standard. The AES algorithm, also known as the Rijndael algorithm, is a symmetric block cipher with a block size of 128 bits. It is converted into ciphertext using keys of 128, 192, or 256 bits. It is implemented in software and hardware throughout the world to encrypt sensitive data. The National Institute of Standards and Technology, also known as NIST, started development on AES in 1997 when it was announced the need for an alternative to the data encryption standard. The new internet needed a replacement for DES because of its small key size. With increasing computing power, it was considered unsafe against entire key search attacks. The triple DES was designed to overcome this problem. However, it was deemed to be too slow to be deployed in machines worldwide. Strong cases were present by the Mars, RC6, Serpent, and the Twofish algorithms, but it was the Rijndael encryption algorithm, also known as AES, which was eventually chosen as the standard symmetric key encryption algorithm to be used. Its selection was formalized with the release of Federal Information Processing Standards Publication 197 in the November of 2001. It was approved by the US Secretary of Commerce. Now that we understand the origin of AES, let us have a look at the features that make AES encryption algorithm unique. The AES algorithm uses a substitution permutation or SP network. It consists of multiple rounds to produce a ciphertext. It has a series of linked operations, including replacing inputs with specific outputs, that is substitutions, and others that involve bit shuffling, which is permutations. At the beginning of the encryption process, we only start out with a single key, which can be either a 128-bit key, a 192-bit key, or a 256-bit key. Eventually, this one key is expanded to be used in multiple rounds throughout the encryption and the decryption cycle. Interestingly, AES performs all its calculations on byte data instead of bit data, as seen in the case of the DES algorithm. Therefore, AES treats 128 bits of a clear text block as 16 bytes. The number of rounds during the encryption process depends on the key size that is being used. The 128-bit key size fixes 10 rounds, the 192-bit key size fixes 12 rounds, and the 256-bit key holds 14 rounds. A round key is required for each of these rounds, but since only one key is input into the algorithm, the single key needs to be expanded to get the key for each round, including the round 0. With so many mathematical calculations going on in the background, there are bound to be a lot of steps throughout the procedure. Let's have a look at the steps followed in AES. Before we move ahead, we need to understand how data is being stored during the process of AES encryption. Everything in the process is stored in a 4x4 matrix format. This matrix is also known as a state array, and we'll be using these state arrays to transmit data from one step to another and from one round to the next round. Each round takes state array as input and gives a state array as output to be transferred into the next round. It is a 16-byte matrix with each cell representing 1 byte, with each 4 bytes representing a word. So every state array will have a total of 4 words representing it. As we previously discussed, we take a single key and expand it to the number of rounds that we need the key to be used in. Let's say the number of rounds are n, then the key has to be expanded to be used with n plus 1 rounds, because the first round is the key 0 round. Let's say n is the number of rounds. The key is expanded to n plus 1 rounds. It is also a state array having 4 words in its vicinity. Every key is used for a single round, and the first key is used as a round key before any round begins. In the very beginning, the plaintext is captured and passed through an XOR function with the round key as a supplement. This key can be considered the first key from the n plus 1 expanded set. Moving on, the state array resulting from the above step is passed on to a byte substitution process. Beyond that, there is a provision to shift rows in the state arrays. Later on, the state array is mixed with a constant matrix to shuffle its column in the mix column segment, after which we add the round key for that particular round. The last 4 steps mentioned are part of every single round that the encryption algorithm goes through. The state arrays are then passed from one round to the next as an input. In the last round, however, we skip the mix columns portion, with the rest of the process remaining unchanged. But what are these byte substitution and row shifting processes? Let's find out regarding each step in more detail. In the first step, the plaintext is stored in a state array and it is XORed with the K0, which is the first key in the expanded key set. This step is performed only once on a block, while being repeated at the end of each round as per iteration demands. The state array is XORed with the key to get a new state array, which is then passed off as input to the sub-bytes process. In the second stage, we have byte substitution. We leverage an X box called as a substitution box to randomly switch data among each element. Every single byte is converted into a hexadecimal value having 2 parts. The first part denotes the row value and the second part denotes the column value. The entire state array is passed through the S box to create a brand new state array, which is then passed off as an input to the row shifting process. The 16 input bytes are replaced by looking at a fixed table given in the design. We finally get a matrix with 4 rows and 4 columns. When it comes to row shifting, each bit in the 4 rows of the matrix is shifted to the left. An entry that is a fall off is reinserted to the right of the line. The change is done as follows. The first line is not moved in any way. The second line is shifted to a single position to the left. The third line is shifted 2 positions to the left, and the fourth line is shifted 3 positions to the left. The result is a new matrix that contains the same 16 bytes but has been moved in relation to each other to boost the complexity of the program. In mix columns, each column of 4 bytes is now replaced using a special mathematical function. The function takes 4 bytes of a column as input and outputs 4 completely new bytes. We will get a new matrix with the same size of 16 bytes, and it should be noted that this phase has not been done in the last round of the iteration. When it comes to adding a round key, the 16 bytes of the matrix are treated as 128 bits and the 128 bits of the round key are XORed. If it is the last round, the output is the ciphertext. If you still have a few rounds remaining, the resulting 128 bits are interpreted as 16 bytes and we start another similar round. Let's take an example to understand how all these processes work. If our plaintext is the string 2192, we first convert it into a hexadecimal format as follows. We use an encryption key which is that's my kung fu, and it is converted into a hexadecimal format as well. As per the guidelines, we use a single key which is then later expanded into n plus 1 number of keys, in which case it's supposed to be 11 keys for 10 different rounds. In round 0, we add the round key. The plaintext is XORed with the case 0 and we get a state array that is passed off as an input to the substitution bytes process. When it comes to the substitution bytes process, we leverage an S box to substitute the elements of each byte with a completely new byte. This way the state array that we receive is passed off as an input to the row shifting process on the next step. When it comes to row shifting, each element is shifted a few places to the left, with the first row being shifted by 0 places, second row by 1 place, third row by 2 places, and the last by 3. The state array that we received from the row shifting is passed off as an input to mix columns. In mix columns, we multiply the state array with a constant matrix, after which I receive a new state array to be passed on to the next step. We add the new state array as an XOR with the round key of the particular iteration. Whatever state array we receive here, it becomes an output for this particular round. Now, since this is the first round of the entire encryption process, the state array that we receive is passed off as an input to the new round. We repeat this process for 10 more rounds and we finally receive a ciphertext. Once the final state array can be denoted in the hexadecimal format, this becomes our final ciphertext that we can use for transferring information from the sender and receiver. Let's take a look at the applications of AES in this world. AES finds most use in the area of wireless security in order to establish a secure mode of authentication between routers and clients. Highly secure mechanisms like WPA and WPA2 PSK are extensively used in securing Wi-Fi endpoints with the help of Rindial's algorithm. It also helps in SSL TLS encryption that is instrumental in encrypting our internet browser sessions. AES works in tandem with other asymmetric encryption algorithms to make sure the web browser and web server are properly configured and use encrypted channels for communication. AES is also prevalent in general file encryption of various formats ranging from critical documents to the media files. Having a large key allows people to encrypt media and decrypt data with maximum security possible. AES is also used for processor security in hardware appliances to prevent machine hijacking, among other things. As a direct successor to the DES algorithm, there are some aspects that AES provides an immediate advantage in. Let us take a look. When it comes to key length, the biggest flaw in DES algorithm was its small length was easily vulnerable by today's standards. AES has managed to nab up 128, 192 and 256-bit key lengths to bolster the security further. The block size is also larger in AES owing to more complexity of the algorithm. The number of rounds in DES is fixed irrespective of the plain text being used. In AES, the number of rounds depends on the key length that is being used for the particular iteration, thereby providing more randomness and complexity in the algorithm. The DES algorithm is considered to be simpler than AES, even though AES beats DES when it comes to relative speed of encryption and decryption. This makes advanced encryption standard much more streamlined to be deployed in frameworks and systems worldwide when it compares to the data encryption standard. Hope you learned something new today. If you have any questions from today's session, be sure to let us know in the comments section below. Subscribe to our channel for more videos like this, and thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.